Welcome back to this critical care training sessions, and the topic of interest today is mechanical ventilations. The basic of mechanical ventilation, I presume that it's a topic to be understood by all the staff working in the ICU. It should be known to the respiratory therapist. Even a medical student should be aware about basics of mechanical ventilation. In the light of recent 2019, we faced the big COVID pandemic and realized the importance of understanding the mechanical ventilation. So, with that intent in mind, I have divided this talk in two parts. The first part will cover the basic terminologies to be understood, understanding the physiology of mechanical ventilation, understanding flow, volume, resistance, and equation of motion of mechanical ventilation, that is physiology of mechanical ventilation. How to set up the initial ventilator, what setting should be put on the patient, and understanding the phase variables, especially the trigger, limit, and cycle, and the baseline variable PEEP. So this will be discussed. In part 2, we'll go for the modes of mechanical ventilation, the advanced modes, and further understanding of PEEP, maybe monitoring and troubleshooting, and ventilator graphics. So let's start with the basic terminology first. What do you do the first thing when you put a patient on a mechanical ventilator? The dial which you touch is the FiO2. Patient has presented with respiratory failure. So the first thing you set is the fraction of inspired oxygen. So what do you understand by fraction of inspired oxygen? So if we say we are taking oxygen on room air, that is 21% oxygen we take on room air. What is the fraction? The fraction of inspired oxygen which we breathe is 21 by 100, that is 0.21. If a patient with respiratory failure, of course we start on ventilator with 100% oxygen, and the FiO2 corresponding is 100 by 100, that is FiO2 of 1. Though we start with highest possible, that is 100% oxygen, our aim is to gradually de-escalate it to the safer zone, as we are aware that even oxygen toxicity, oxygen free radicals because of hyperoxia, is deleterious to the patient. So our aim is to reduce it to the safer level as early as possible to FiO2 of say 0.6 or 60% FiO2. How do we achieve this in ARDS or patients with other pathologies? We target and monitor SpO2, that is saturation of pulse oximeter, or you can do it guided by the partial pressure of oxygen in millimeter of mercury in arterial blood gas analysis. The SpO2 target is never 100%. In ARDS, like we keep a target of 88 to say 92%, or PaO2 of say 55 to 60 in ARDS patient. So as per the disease condition, you should target that SpO2 and PaO2 and gradually dial down your FiO2 to the safer level. That is the first important of understanding the fraction of inspired oxygen. It also helps in calculating, which we discussed in ABG session earlier in our critical care training session, that is P by F ratio, that's PaO2 by FiO2 ratio. So normally if we say a patient with PaO2 of 60 millimeter of mercury and it is say on the room air, that is fraction of inspired oxygen is 0.20 or 0.20 for calculation purpose, or you can take 0.21. You will achieve a PF ratio of 300, which is considered normal. So 300 to 200 is a mild respiratory distress, so mild ARDS. 200 is moderate, and less than PF ratio of less than 100 is severe ARDS. So you can categorize the severity of respiratory failure based on knowing the fraction of inspired oxygen and PaO2 values. If you are in resource limited setting, okay, you can calculate the saturation by FiO2 ratio similarly. So lower SpO2 by FiO2 ratio will be surrogate of PaO2 by FiO2 ratio and will help you to classify the respiratory failure. So this is the first terminology of importance to understand about the PF ratio, SpO2 FiO2 ratio, and understanding the fraction of inspired oxygen. That is let's go to the next terminology. So the next is the rate of respiration. The rate of respiration will decide about the ventilation, minute ventilation. So you know that respiratory rate has gained importance in present era, very much important, because it is also considered as one of the parameter which can induce induced lung injury. It is one of the important component, and so respiratory rate, setting of respiratory rate is very important when you initiate a mechanical ventilation. The basic physiology you should know is respiratory rate into tidal volume gives you what you call as minute ventilation. Normally the minute ventilation as per the weight, if you see in a 60 kg, should be 6 liter, so 60 into 100 ml per kg. So the respiratory rate, if I set on a ventilator, say 20 breaths per minute I have set in a patient. So what does mean 20 breaths in 1 second, 1 minute, that is 60 seconds. So one breath will be around 60 by 20, that is 3 seconds. So one breath is delivered every 3 seconds. Why it is important? We know that our inspiratory by expiratory ratio, normally we have inspiration of 1 second, expiration of 2 seconds. So IE ratio is 1:2. So here 1 second is inspiration and 2 seconds is expiration. Expiration is passive on mechanical ventilator. Inspiration is what the flow is generated and actively given to the patient. What is the effect of increasing respiratory rate? Suppose the respiratory rate goes up to 30 per minute. What will happen is your inspiratory time 60 by 30 will become 2 seconds. What is affected in I ratio is the expiratory time. So your inspiratory time remains 1 second, expiratory time becomes 1 second. So there may be air trapping, or there may be generation of auto PEEP, and this effect of, because of increased respiratory rate, you should be aware about this phenomena. So this is the important thing to understand about the respiratory rate, which is also now included in calculation of mechanical power. So respiratory rate you decide as per the partial pressure of carbon dioxide. So CO2 you want to keep. In ABG session we have discussed about the normocapnia, so you aim for normocapnia, or in ARDS patients sometimes you accept this permissive hypercapnia, and then you set your rate accordingly as per the disease condition. Now let's go to the third important parameter, that is tidal volume. What is tidal volume? So setting of tidal volume in mechanical ventilation. So tidal volume is the amount of air which goes in and which goes out during normal respiration, and it is said that 6 to 8 ml per kg even for the normal lung is what you said. Now remember, this per kg or body weight, this kg per kg body weight is not the actual body weight. Suppose I am 60 kg now and I don't exercise and I become say 100 kg and my weight increases to 100 kg. This doesn't reflect on my lungs. So 60 kg, my actual body weight has to be calculated as per the height. So as per the height, I will calculate my ideal body weight and then will dial the tidal volume to 8 ml per kg of body weight. So as per the actual body weight, if you dial, you will end up in causing the ventilator induced lung injury. So always take into consideration the height of the patient, and there are formulas like for male height 50 plus 0.9 times height in centimeter of the patient minus 150 is the ideal body weight for that height of the patient, and then with that you calculate as per the tidal volume. So this is very important point in setting up the tidal volume as per the ideal body weight as per the height. For females it is 45.5 plus 0.9 times height in centimeter minus 145. So you have to use these formulas are available. You have to use this to calculate the ideal body weight and then dial the tidal volume as per the ideal body weight of the patient to prevent the deleterious, what is called as volotrauma. Now next important terminology is the sensitivity. Sensitivity or trigger sensitivity, one of the phase variable which you are going to see is how the ventilator responds to the patient effort. So patient demand. So if you keep the sensitivity very low, so there may be the machine will trigger the respiration even though it was not the patient effort. So you have to keep the sensitivity ideally minus 2 centimeter of pressure sensitivity in trigger we keep, and flow sensitivity of 4 to 5 liters, so that ventilator responds to the patient effort. That is we'll discuss in phase variable. Then another thing is the peak flow, the maximum flow rate used to deliver each breath to the patient, usually in liters per minute. So depending upon the disease condition, patient may require flow rate from 40 liter per minute to 80 liter per minute. So how is his drive, that will decide the peak in flow rates to be set on the ventilator. Inspiratory time we have already seen, as the respiratory rate increases, the expiratory time is affected. The inspiratory time remains the same. It includes the inspiratory phase of the ventilator cycle. And IE ratio is important when you are setting a patient for, say, COPD patient, chronic obstructive pulmonary disease, where the expiratory phase is prolonged. And if you keep a high respiratory rate, you are bound to get a air trapping or a dynamic hyperinflation, and their setting of IE ratio and a respiratory rate on a lower side, not very high rate, is very important. Then coming to the flow pattern, these we'll learn in the ventilator graphics, but you should know the flow patterns like scare flow wave pattern. If you have a flow pattern on the flow and time curve, so x-axis there is time, here is a flow, and if you have this type of scare wave pattern of inspiratory flow pattern, that is seen in the volume control mode of ventilation, which is flow cycle, and the expiration is seen as it's a passive process, so it is exponential decay. You can see here is the expiratory limb. This is the expiratory limb. If you see a sinusoidal pattern, this is mostly seen in the spontaneous respiration. This small below the baseline here, you see the trigger, that is the negative trigger. You may have a exponential decay or decelerating pattern. This is seen in the pressure control, this is in the volume control, this is the spontaneous. This way flow patterns we'll see in the ventilator graphics. Then positive and expiratory pressure, that is the pressure at the end of expiration to keep the alveoli open. So this positive and expiratory pressure is a baseline variable which prevents the alveolar collapse at the end of expiration, and it is important to improve the oxygenation and homogenization and reduce the VQ mismatch. And it is very important to keep a positive and expiratory pressure in a patient when you are weaning a COPD patient, so that they overcome their auto PEEP and it will help to wean the patient. But when the patient is on mechanical ventilation, control mode of ventilation, COPD patient, there typically we keep a positive ZEEP, that is zero and expiratory pressure, in control mode. But in weaning mode you have to add a PEEP to reduce the work of breathing. That we'll see in when we discuss the mode. Normally they say that at the end of expiration the vocal cord align together and we develop in normal respiration. Also we have physiological PEEP, that is of 4 centimeter of water. So once we have understood this ventilator terminology, let's go to the equation of motion of mechanical ventilation. So see as a single compartment model. So this is a tube. So trachea is a tube and it's divided into bronchi, bronchioles. We take for understanding a single compartment model tube and a balloon at the end, that is the alveoli. So what drives the air in is the pressure. So here is the pressure, that is the total pressure, and this total pressure at this end, which drives the flow of air into the tube, will depend upon the ventilator pressure, which is generated by ventilator positive pressure, plus the P muscle pressure. That is, P muscle is the pressure generated by the patient in assisted ventilation. He'll withdraw the diaphragm down to breathe in and take in the air. So these two pressure work in sync to cause the respiration in the patient, which is equivalent to as the flow. And if there is a pressure drop here, that is change in flow by change in pressure, that is flow into resistance. So depends upon the resistance, flow into resistance, plus the elastance of this. So the ability of this alveoli to open, that is elasticity, into volume, plus the amount of air which remains in the lung after expiration, that is positive and expiratory pressure. Now try to understand the components. So the pressure, total pressure, P vent plus P mus is equal to flow into resistance plus elastance. The opposite of elastance, ability to distance, is the elastance. The ability of this alveoli to distance, if it is highly elastic, very able to distance, like in COPD patient, the compliance will be low. So elastance is opposite of compliance. So the ability to distend is poor, then it's a poor compliance. So elastance is a opposite of compliance. So we can say volume by compliance here, plus the positive and expiratory pressure. So what is to understand here is when you dial a mode on a ventilator, suppose you dial a volume control mode. Now volume control mode is a flow cycle. So flow is fixed here, volume is fixed. You are dialing 6 ml per kg, volume is fixed, flow is fixed. The variable which is not under your control is the, which you have to monitor, is the pressure. So total airway pressure or peak airway pressure you have to monitor in the patient, and it will depend upon the resistance and the positive and expiratory pressure. So you can have two control variable, but the other will be independent variable. Similarly, if I take a pressure control mode where this variable is under control, you have to monitor the volume, which may be variable depending upon the compliance. So this is very basic equation of motion of mechanical ventilation, which helps you understand the relationship between the pressure, the flow, the resistance, the volume, compliance, and the P, that is positive and expiratory pressure. Now coming to the phase variables, as I told, there are 3 phase variables. One is trigger. Trigger is the one which initiates the ventilation, which the ventilator sense that patient has demanded for inspiration, the inspiratory valve opens. So if I plot this pressure and time curve here, and the patient generates this negative pressure here, trigger, that is a trigger, and the flow is generated, reach the peak pressure, plateau pressure, and then come to the baseline. So this is the trigger variable here. So that is -2 centimeter of water if I kept on a ventilator, and if patient generates -2, the flow will be generated, and this is the pressure trigger. The next trigger which you can keep, which is in studies has shown to cause less work of breathing, is a flow trigger, where you can keep a flow of 5 liter per minute in the circuit. If there is a flow is detected, the machine senses that inspiration is required, and the inspiratory valve opens, and the patient gets the breathing. So in flow time curve, if this is time and flow, the initial flow generated by the patient, 4 to 5 liters, will be depicted by some color here. So patient has triggered, and then the flow is generated till the inspiration limit, volume limit, and cycles to expiration. So this is the flow trigger. So trigger sensitivity is important when you keep in your patient. Try to see that you don't keep a very low trigger. So suppose I keep -1 centimeter. If my circuit leak is there, or even if there is a cardiac oscillation, it will sense as a patient demand for respiration, and you will end up getting auto triggering in this patient. This we'll discuss in ventilator graphics, of course. But at present moment, try to understand what is trigger. Second is the second phase variable is the inspiratory flow cycle. So inspiratory flow, trigger flow is the it starts after the trigger till the limit is reached. This is limit does not decide the expiration. Limit decides the inspiratory flow. So the patient has opened the valve, triggered, the flow starts, and it is reached a constant volume. Suppose you have set a volume limit of 500, the volume is reached, now it will cycle to expiration. So this is cycling phase. This is first is the trigger phase, second is the limit phase. So limit is either volume limit or the pressure limit. So whenever the set limit is reached and the delivered tidal volume is delivered, then there will be cycling variable where the inspiratory phase is converted to expiratory phase now, and cycles to expiration. And expiration, as I told, it is a passive process, and this is the exponential decay waveform you see on the ventilator. So trigger, limit, and cycle, and last baseline variable is a positive and expiratory pressure. That is this flow, this pressure will not reach to the baseline here, but it will have certain pressure inside at the end of expiration. If you give the expiratory hold, you can see that positive and expiratory pressure, whatever you have kept, 4, 5 or 8, depending upon the requirement of the patient. So PEEP is the baseline variable. So these phase variables are important for synchrony of the patient during mechanical ventilation. So you should check what trigger you have kept, whether it is flow trigger or pressure trigger, what is the limit you have kept, and what is the how is the cycling of the patient. Like in pressure support mode, the cycling is flow cycle. So the flow will increase, and when it start decaying, suppose it reached the 25% you have kept, the decline in flow is 25% of the baseline, it will cycle to expiration. And that is seen in the spontaneous or in the patient with pressure support mode of ventilation. That again we will revise in our ventilator graphics. Now understand the mode. So first I told you the basic modes of mechanical ventilation: volume preset or pressure preset. In equation of motion we have understood that if we keep the volume set mode of ventilation, so it is flow cycled, and what is you have to monitor is the peak pressure and the plateau pressure. Plateau pressure you will check when there is no flow. So at the end of inspiration, if you hold the inspiratory hold button, there is no flow. So flow, if you go back here, if you see our one compartment model, if there is no flow here, so you have kept a flow of 0 into resistance, What pressure is monitored at the end of inspiration here is the alveolar pressure, that is the P flat of alveolar pressure. So that you see in the volume control mode of ventilation. If it is a pressure control mode of ventilation, depending upon the compliance of the lung, the volume will vary and you have to keep a watch on the volume. Cycling, we know that change from inspiration to expiration, it will be depending on the amount of volume limit or pressure limit, or the flow cycling as seen in the pressure support mode. Expiration, phase of breath start from expiration flow to start of the next inspiratory flow, that is expiration. Inspiration is a phase of breath which start from inspiratory flow to start of expiratory flow. It may include the inspiratory pause here. Intermittent mandatory ventilation is the time cycle. Sometimes if you keep the patient on SIMV mode, synchronized intermittent mandatory or intermittent mandatory, and you have set a respirator of 20, that is 20 breaths per minute, that is one breath every 3 seconds, and if your I ratio is 1:2, so after every second the breath will be initiated. There is time cycle intermittent mandatory breath. Mandatory breath is the machine breath in which machine is triggered and machine cycled. Spontaneous breath is breath which is triggered by the patient and patient cycle. Trigger is a phase variable we understood. To start inspiration is either a pressure trigger or a flow trigger. Coming to the mode of ventilation, just a revision. Nowadays we use this dual mode, that is pressure regulated volume control, or you may set volume control or pressure control, but you should know that what the mode you are familiar with. Now tidal volume you keep around 6 to 8 ml per kg. I already explained that this should be as per the ideal body weight, as per calculation of the height. Start calculating the height of the patient, start calculating the ideal body weight, and don't ventilate the patient with actual body weight. That will cause volutrauma. Respiratory rate has to be set as per the disease condition. As I told, in COPD patient, expiratory time is likely to be prolonged, so keeping a high rate will lead to dynamic hyperinflation. In normal adult, you can keep a respirator of 20-24. See the minute ventilation requirement of the patient, what disease condition is in, and monitor your ventilation with PCO2 and set your respiratory rate. Mode can be flow cycle, decelerating, accelerating. The flow has to be checked. In patient with high demand of respiration, the flow requirement may be up to 80 liters. FiO2, as I told, dial it to the non-toxic FiO2 as early as possible. Setting of PEEP, that is a baseline variable, positive and expiratory pressure, and normal physiological PEEP of 4 or 5, I have told you, is very important to maintain the oxygenation. You have to find the optimum PEEP. Now in advanced mode we will see that in advanced next session of this lecture we will see how to set up the PEEP. But remember that positive and expiratory pressure has some hemodynamic consequences as well, and there is a heart-lung interaction during this mechanical ventilation which we are going to study. So the setting of PEEP is as per the saturation, as per the tolerance of the patient, and to get the optimum PEEP where you get the good saturation without hemodynamic compromise. This we will study in the in the second session of the mechanical ventilation lecture. The last before ending up, we should know one terminology: transpulmonary pressure. So what is transpulmonary pressure is another important factor which helps us in understanding ventilator mechanics and reducing the ventilator induced lung injury. Most of the new ventilators like Hamilton have the ability to, in advanced setting, you can monitor transpulmonary pressure and set your positive and expiratory pressure according to it. So transpulmonary pressure can be measured by esophageal balloon with the esophageal probe kept in the esophagus, which is a surrogate of transpulmonary pressure. So first let's understand what is transpulmonary pressure. Transpulmonary pressure is one which distends the alveoli. So we have chamber within chamber. So we have alveoli and we have a pleural space around. So pressure here is ideally negative and this is positive, and this helps to distend the alveoli during inspiration. So that is the transpulmonary pressure. If the transpulmonary pressure become positive, that is TPP is equal to alveolar pressure minus intrapleural pressure. This is intrapleural pressure. So intrapleural pressure increases and above your alveolar pressure, then transpulmonary pressure becomes low. In that case, you will develop atelectasis or collapse of the alveoli. So that's what we don't want. So in patients with like ascites or raised abdominal pressure, which is reflected as increase in the intrapleural pressure, in such cases you may have to keep a baseline PEEP of say 8 to 10 centimeter of water to prevent this phenomena of collapse of the alveoli. So remember, transpulmonary pressure is a pressure difference between the alveolar pressure and the surrounding intrapleural pressure, which has to be kept positive. If it becomes low or negative, then you develop a collapse. That's for today in the basics of mechanical ventilation. See you in the next session 2 to understand the more details. Till that time, any queries you can give at practicaltips7gmail.com. Thank you very much.